On to our next whole lot of lab. And in this video, we're going to talk about viscosity, which is ASTMD 445. Viscosity, you probably, if you've taken another science course, and especially maybe like an intro to chemistry, general chemistry class, viscosity is this idea that liquids can be very thick and resistant to flow. That's what viscosity is all about. So for instance, I can take water in a cup and I can pour it out quite easily. It will just poof everywhere, all in the floor, and I get a laugh because I made a mess. Well, then if I can take honey, which is also a liquid, and that honey goes into a cup, and I turn that honey cup upside down, I'm going to wait and wait and wait and wait and wait a little bit longer, if it's good quality honey, for it to pour. So it is more resistant to flow. Therefore, honey would have a higher viscosity value than something like water. So in theory, you probably have talked about viscosity reads before, and you're like, ooh, this one has a higher viscosity than this one because this one is thicker than this solution over here. But for the first time, maybe this is going to be your chance to actually assign a number to viscosity. So if we talk about it in theory, and if we can compare and contrast, then we should be able to calculate some type of theoretical value that we can use as kind of mathematical proof that this one is thicker than this one, or this one is more viscous than this one. And this is what this equation is all about. All right, so what happens in a viscosity test? Well, first off, you can use what we call a viscosimeter in order to do the test. This is injecting the liquid onto a machine, almost like a density meter, and then allowing the instrument to do what it needs to do, and it will pop you out an answer on the viscosity of that liquid solution. That is not a big deal, but the problem, we don't have one. So, in the meantime, we've got to go a little bit more old school, like how they used to do it back in the day. And there were two different options here for viscosity reads. One was an Ottwald and the other one was a Ubelode piece of glassware. We like the Ubelodes, and there's slight differences between these. They're both used in pretty much the same similar way, or the idea or the concept. It's just a matter of how do I suck the sample up into the tube and how do I let it drain. That's really the major difference between the two here. And for that reason, I'm actually going to show you this first in person when you eventually make it to the viscosity reading. So I'll demonstrate it once, and then you can follow after me after that fact. For now, though, general kind of rule of thumb, what goes on. The pieces of glassware that measure viscosity is most of the time shaped like a U, all right? Now, there's a difference that happens maybe over here on the right-hand side, but that is perfectly fine. We're just general speaking right now, and that's it. So what happens is that I will take my sample, and that sample in this case is going to be my biodiesel, and I'm going to add the sample to the piece of glassware that we will use to measure viscosity with. And then I'm going to keep adding it until I get to the line. This line is a fill line. So once I get to that moment, then this is going to be enough sample for me to do something with. So I keep adding, I keep adding, I keep adding, and then sooner or later I'll get, it's like a volumetric flask or, you know, something like that. I'll get to the line that's etched on the piece of glassware, and that is my fill mark. On the other side, normally what happens is that we take something like a pipette bulb, and the pipette bulb will be plunked down on top of that piece of glassware, and we will use it like we use a pipette bulb when we measure using volumetric pipettes. We let go of the air pocket that we've created, and that will suck sample up into that side of the piece of glassware. So, whoop, up it goes, right? So there's often two lines that are going to be located over here on the right-hand side, and those two lines are going to be pretty important. So there's going to be a line here at the top and typically one below that. All right, so what's going to happen is that I'm going to take my biodiesel, and I normally, when I use these types of pieces of glassware, I normally will go above the top line. So I'll suck my sample up here closer to the pipette bulb, but not all the way. I don't want my sample up into the bulb, right? So once I go over that top line, then what's going to happen is I'm going to take my pipette bulb and I take it off of the piece of glassware. So when I take the suction off, it goes down, 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 down. It starts to drain back to where it came from, right? So what happens is that when it reaches spot number 1, and that spot number 1 is the highest mark up here at the very top, when that biodiesel drains to that first mark right here at the very top, this is where my timer starts, because we are going to measure the time it takes to drain. And the time it takes to drain is going to be located between these two markings over on the right-hand side. So when that biodiesel drains to that first mark, that is when I hit my timer, and that's why I go over the first mark. It gives me enough time to take the bulb off, and it gives me enough time to grab a hold of the timer and then allow me to press the start button for when it reaches that beginning mark. So when it drains to the first, spot number 1, I start my time, and then I wait. Wait until it hits this second line, and when it hits that second line, this is where I stop the timer. So I am recording time that it takes for a sample to drain in between two markings, a beginning and an end over on the right hand side. The fill line over on the left hand side, this fill line is stamped to let you know this is how much of your sample is going to be needed in order to go above this line and allow it to drain with no air pockets that get on the inside of this thing. So that's why the marking on the left is also very important. So the fill line, I have to do that first. Once I have enough sample in the piece of glassware, I take a pipette bulb and I suck that sample up into that side of the piece of glassware. I go over the top line and then I allow it to drain. When it goes to the start mark, I click my stopwatch and I start recording the time. And then when it hits that second line, that is where my time stops, and I write down that time interval. This time interval can simply be seconds, right? It could take that quick for those samples to drain between those two lines, the beginning and the end. That's perfectly okay, and we assume that it should not take a long time because the unit that is used in viscosity, look, is in terms of second. So that's actually the unit that we need to be in. However, there are times that this will take minutes in order to drain between the two marks. So let's say 3 minutes and 45 seconds is what I'm going to see with my timer. That's not a big deal. I need to convert my minute over into seconds, right? And I do this because I know that for every 1 minute, there's 60 seconds. So what will happen here is that I'll take 3 minutes and I'll times by 60, which is 180. And then another 45 seconds gets added on top of that. And that 180 plus 45 will give me my total time. Whatever the case is, your unit needs to be full-blown second that you will use for this equation. All right. So if you need help with the conversion or you want me to double check it, I'll be glad to, but it's simply 60 seconds for every minute if you do go over the 1 minute mark. All right, so what's going to happen here is that we are measuring the distance that's traveled. Notice the unit says millimeter second squared, all right? Or millimeter squared per second, sorry. So we're looking at distance and we're looking at time for that distance. And this is going to give me a range of 1.9 to 6. So there's a lot of wiggle room here. Biodiesel, slight differences here can really make it or break it for you. So very often these viscosity values, they are going to be a little bit larger as far as a window goes, because it doesn't take a lot in order to get this number to change quite drastically. So in order to calculate the viscosity here, what's going to happen is that I will take N sub W. And N sub W down here at the bottom says it's the viscosity of distilled water at 40 degrees. Oh my God, 40 degrees. So 0.6579. I'm going to come back to that temperature in just a minute. All right. So that is going to go in for NW. It's just the number. That's all that is. So 0.6579 is going to go in for NW. Next up is P sub S. and that's the density of the sample. So this is another reason that we do our density meter read and why we record density as well as specific gravity, right? We're going to have to use the density here for this particular equation. So whatever I get from the density meter, that goes in for D or P sub S. Next up is T sub S, and it says that is the time that's required in seconds by the sample to cover the distance that's stamped on the glassware. So time is in terms of second, and that will be time that it took for my biodiesel to go from beginning to end. Down here at the bottom is PW, and PW, that's actually rho, not a P. So that PW, that's the density of distilled water. And that density of distilled water, well, we can find that in a textbook value. We can find that on Wikipedia, on Google, but it is the density of water at 40 degrees because that is the measurement that the viscosity needs to happen at with this particular sample. So I need the density of distilled water at 40. If you want to use the density meter to do this, you can, but again, it's quite easy to find this type of value on Wikipedia or Google. Next up is T sub W, and that is the time required in seconds by distilled water to cover the same distance. All right. So the top piece is mainly sample driven, and the bottom is mainly water driven. If I have those values and I plug them in, I can calculate a value for viscosity, and that value for viscosity should be between 1.9 to 6. All right, now what happens when I use something like a U-boat load is that one time through is never really good enough. So I really like to do these in triplicates and take a nice average. So what will happen here is that I want to make sure that I have the appropriate temperature of the water when I make this measurement. So the density of the water is going to be used, but it's the density at 40, right? And the viscosity of the water is going to be used, but it's the viscosity at 40. So 40 is going to be tying my hands, and I cannot use any other temperature other than that. So I need to make sure that the temperature of water is close to 40 degrees here. Most of the time, we can easily accomplish this by placing it into a water bath. But that also means that my glassware that I use for the viscosity needs to go into a water bath as well. So this whole thing is going to be lowered down into a beaker, and that beaker is going to held constant at 40 degrees. So that way my water stays at 40 and my biodiesel sample stays at 40. If I put warm water or warm biodiesel in a piece of cold glassware, my temperature changes and my values can change as well, and I cannot afford that to happen here. So 40 degrees is where it's at. So I'm going to heat this water up to 40, and then I'm going to place that into the U-boat load or the type of viscosimeter that we are using, and then I will suck it up and make a time. Suck it up, make a time. Suck it up, make a time. So these three total number of seconds will get averaged, and that average will go here for the average time that it took for water to drain. All right. Next up is the temperature of biodiesel. Just like with water, I need everything to be consistent because we need to compare apples to apples. So once more, I need to put my biodiesel into a water bath held at 40 degrees. My U-boat load needs to be at 40, or again, whatever piece of glassware that I'm using for this. And then that way, when I place the biodiesel into the piece of glassware, a drastic temperature change is not going to happen. So the same thing's going to happen with my biodiesel. I suck it up and let it drain. Suck it up and let it drain. And suck it up and let it drain. And I do that 3 times. And I get, yet again, another average. So this will be my average time for my biodiesel. That's the average time for the water sample to drain in the piece of glassware that I'm using. Once I have those values, then it's pretty easy. I go up here at the top, and that N sub W stays as 0.6579. That's why we gave you that value in terms of 40 degrees. My P sub S, again, that's the density of the sample. The T sub S, that is the time that I calculated on average down below. My P sub W is the density of water at 40 degrees. That can be looked up. And then T sub W, that is the time required by water to go the distance, and that is the average calculated down below. All right, so once I do that, I calculate one viscosity value based on the averages, and that one viscosity value hopefully will fit in the range of 1.9 to 6. So you're going to see the same question down here at the bottom. Does it pass the accepted value? The answer is yes or no, and use that as a guideline to go by. Next up, another test that we're going to do with the biodiesel, whole lotta, is the titration of a soap content. So there could be residual soap that is left over, and soap is going to be a two-stepper here. The first part is making sure that you don't have any catalyst that is left, and after you determine there's no catalyst left, then you go and you take a look at the soap amount that we will begin to titrate, because the catalyst will interfere with the soap if you don't make sure that all the catalyst is neutralized and out of there before you begin the titration. All right. ASTM standard, if you made it with potassium hydroxide, and we did, it is 66 part per million. That is the guide that we need for this value to pass. The reason that it says this is because potassium hydroxide is not the only base that we can use for the reaction to go forward. We can use something like sodium hydroxide instead of KOH. And NaOH, if it's used, actually gives you a different threshold value because of how that reaction takes place. So because we've used KOH, it's been written for KOH, we use the number in regards to KOH, and in that case, it is 66 ppm. That's what we want to see, or lower. All right. Part A, the test for residual catalyst. This is actually going to be pretty easy. It's just going to take a little bit of prep on your part in order to get this done. Number one says pour 100 mils of IPA, which is rubbing alcohol, into a 250 ml beaker. Pour 100 mils. This does not need to be pipetted. This can be a graduated cylinder. Place it on the balance and tare it. So what's happening is that I'm getting ready to create a nice little swimming pool for my sample to jump into. And we are going to be determining this based on mass of the biodiesel. So I need to tare out the mass of the IPA before I go any further. Number two, place it on the balance, tare it. Number three, add 10 grams of your biodiesel. So while you are there in front of the balance and you're reading the digital readout, you are going to add squirts of biodiesel into that beaker until you get close to 10 grams. Write down the actual amount that you are using, because that's going to be very important, but you need something close to 10 in order for this to kind of work out the proper way. So 10 grams plus or minus. Number four, it says add 5 drops of 1% phenolphthalein solution. This phenolphthalein will probably be made for you. This is an indicator that we keep in stock all the time. That indicator is just going to do what that indicator has always done if you've taken 114 and 115. This is an indicator traditionally used for an acid-base titration. And if it is pink, what happens is that means that you are at the base level of the pH scale. So what you're seeing here is the phenolphthalein color change at the bottom of this page. So colorless in acidic pH environments. So colorless on pH of 0, 1, 2, 3, 4, 5, 6, and even 7. Then when you get to pH of around 8 to 8.5, that is where you see this color change take place, and we get that nice kind of baby pink color in the beginning, and then we get big fuchsia bright pink colors toward the end of that, and that's of course something that we don't want. So there should not be any KOH or any type of catalyst that is going to be left over. And remember, KOH was our catalyst that we used. Methanol was the reagent. KOH was used as a catalyst to get this reaction to go forward a little bit better. So that's what we're kind of making sure of. We don't want this to turn basic. We don't want this to turn pink. And if it does, then we need to fix that before we go further. So it says if the liquid stays clear, there is no catalyst that's left over in your biodiesel because you're not basic, and you can proceed to the next part. If it does go basic, though, you need to kill out that base. You need to kill out that KOH. And you're going to do that by adding a little bit of HCl. And that will typically be ready for you if you need it. It is something that we keep in a big, huge jug. So that way, if you do need to add it, not a big deal. Add a few drops or a few milliliters until that KOH disappears. and your pink color goes to colorless, because that's what we need to do before we go on to part B. So this is testing for the residual catalyst, and it's really just eyeballing it to make sure it is not in a base environment. That is what this is all about. So if KHP gets it to turn pink, add a little bit of acid until it's no longer pink. If you add the KHP and it does not go pink in the very beginning, that's great. It shouldn't. So go on to part B and you can pick up from there. All right, so mass of the biodiesel used, that is an area for you to write down your actual mass from the balance. And then, did the sample turn pink when phenolphthalein was added? Yes or no? Once you get that taken care of, we're now ready for part B, which is the residual soap titration. All right, so for the residual soap, this is something that we would regard as a contaminant that should not be present. So therefore, the soap amount should have a very low value. All right, so if I go back up to the top of this test, it says if made with potassium hydroxide, it should be less than 66 part per million. That is the answer or the number that I should get, or lower. So that is the purpose of part B. So part A was just a check to make sure no KOH is actually going to interfere here. And then part B is specifically for soap, which could also act in a strange about way through the reaction as another base. So from the solution from above, part A, test for residual catalyst, we're going to add 10 to 15 drops of bromophenol blue, and the solution should be a blue-green color. All right, so keep in mind that that solution had your biodiesel in it, it had isopropyl alcohol in it, and it had phenolphthalein already. And you should have ended up with a colorless solution in the end. So we're going to take that same container, we're not going to do anything else with it, then we're going to grab that container from part A, and then we're going to add 10 to 15 drops of another indicator on top of that. And that 10 to 15 drops of other indicator is BPB, bromophenol blue. Next, number 2, it says titrate the solution with a very weak solution of hydrochloric acid until it turns yellow. So this is not going to take a lot of time at all. So notice in step 3, it says add 1 drop at a time. Don't be surprised if it takes less than 1 milliliter here. All right. If it takes less than 1 mil, that's perfectly fine, because it should not have a lot of soap and it should not require a lot of titrant. But do go slow and do 1 drop at a time. Do 1 drop at a time, because that will allow you to get this color change that you're after a little bit better. This yellow color, it will be immediate. You will see it. There's no lag time, but at least go slow with the drops and do 1 drop at a time to get the best results. All right. It gives you an equation. The equation's kind of laid out here for you. B is going to represent the milliliters of the hydrochloric acid that you added. So straight up mils from the burette. 0.01, of course, is the concentration of the HCl that you have used. The C value is the catalyst factor. And because we've used KOH, we're going to use 320.56 for that number. So that is a constant. We're going to plug that number into that location, and that's what we're after. That KOH doesn't have to be KOH. Again, it can be something like NaOH. That's also approved, and it can make the reaction go forward. But because that's NaOH, we would use a different value, because sodium hydroxide would use instead of potassium hydroxide. But 320.56 is what we'll use in this case. W is going to be the grams of the biodiesel in solution. So yet again, why it's very important to record that actual amount from the part A part of the procedure. So all of those go into the equation. Solve the top first, do it in baby steps, and then do the bottom second, and then do the division between those two numbers in order to get a value. Once you get a value, that is not your answer, ladies and gentlemen. Once you get a value, you're going to take that number and you're going to multiply by 1 million. And the reason is because we need to convert it over to part per million in order for this to work. And the number that I get from that equation is not part per million. The number that I get to that equation is actually a step in the right direction, but it's not the end result. So in order to get me part per million, I'm going to multiply that by 1 million in order to convert that number over into something that's kind of makes sense as far as the unit goes. Below 200 is great. 2 to 300 is minimal. So, you know, that's minimal to be approved to be used. 3 to 400, you're starting to see clog problems here. So that definitely has to be taken care of. 400 to 500, this has very high soap content. This is not recommended at all for any purpose. And then greater than 500, you might as well forget it. You might as well start all over. No, you can keep washing, get the residual soap out. Very often that's a way to fix all of these problems. Your washing technique was just not good enough or long enough. So you got to go through, you got to wash, you got to clean, wash and 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 clean, until you get a better product in the very end here. All right, so hopefully you'll get 66 or below, because that is the threshold for this B100 test by the ASTM. The data sheet, pretty simple here at the very bottom. The color of the solution when bromophenol blue was added, what was the start volume on your burette, what was the end volume on your burette, what was the color of the solution after you stopped the titration, and then what is the concentration of the soap in the biodiesel, and that is in ppm. So please do not forget to multiply by 100 in order to get that value. So finally, like all the others, does it pass the accepted value? And the answer is yes or no. And then once you determine that, you move on to your last test, and that's yet again another titration. So we'll again do this one by hand, and it will be very quick and easy, but we'll talk about this in the next video, because this one's going to require a little bit more prep on your behalf.